The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for joining us for Building Resilient Systems with Consul webinar. My name is Yana Baruda, and I'm the Director of Events at HashiCorp. And my colleague James, he is a software engineer at HashiCorp, and he's the lead engineer on Consul and Serif. He has worked on a wide range of projects from large-scale web apps to real-time embedded systems, and he has a particular passion for distributed systems. Um, the format of today's webinar will be, quick introductions, which I just finished, a presentation by James, followed by a demonstration, and then we ask for everyone to, during the presentation, to type in questions, and then we'll answer all of your questions at the end of this presentation. James, it's all yours.
Hey everyone, thanks for attending. So let's jump into the presentation. So we're going to cover kind of a high-level overview of Consul kind of quickly. I'm sort of assuming that most people are familiar with Consul at some level, but we'll do a quick review. Then we'll jump into some architecture details on Consul. We'll talk about a use case around distributed logs. And then we'll revisit Consul's architecture in the context of multiple data centers. And then we'll go through a use case around prepared queries, which is a useful application once you've got things spanning multiple data centers. So let's start with a quick Consul overview. At a glance, Consul has sort of three pillars. One is service configuration and discovery. Two is monitoring at scale, and three is high availability. And we'll go through each of these in a little bit of detail. So at its core, Consul's about service configuration and discovery. So sort of the basic concept of operations here is that you register your services with Consul, and at sort of the most basic level, a service is an IP address and a port number. You can do that via configuration files or through APIs, HTTP REST-style APIs. And then all the machines in your cluster can discover services via DNS or similar APIs. So Consul becomes a source of truth for where all your services are located in your cluster. Consul lets you perform load balancing by shuffling the results when it answers DNS queries. And then Consul lets you manage dynamic configuration via the key value store. So this is useful for sort of application-specific configuration keys, IP whitelist, IP blacklist, all kinds of applications there through sort of a general purpose key value store. And then on top of the key value store, we've built coordination primitives, things like blocking. We'll get into some examples later, and we'll talk in detail about what sessions are as well. And one of the most interesting things about Consul is that it has a lot of ways to integrate with existing apps. So through its DNS interface, you can get essentially a zero-touch integration with any application that can look up a host name. We also support things like server records to look up port numbers. You can do deeper integrations with APIs. So a lot of applications will talk to a REST API. Shell scripts will talk to APIs with things like curl and wget. There's deeper integration with a lot of client libraries. So we have a Golang client library for Consul that's integrated in applications. So we'll talk about some of the tools here, like Consul template and Consul. So the Consul template takes information from Consul, renders config files, and restarts services. And Consul can take information from Consul and set environment variables. So there's a lot of ways to get the service information that's in Consul out of Consul and into your applications. The second pillar was monitoring at scale. So there are some interesting architectural choices in Consul that let it manage health checking across your whole cluster in a scalable way. So we'll talk about this in a little more detail in the architecture section, but there's a gossip layer that gives you sort of a baseline liveness check for all the nodes in your cluster. And that's built into Consul, and it's something that's kind of happening in the background all the time. And then with each service you've registered, or each node that's in your cluster, you can register node and service-specific checks. So these are, you can have Nagios-compatible scripts. You can reuse Nagios scripts directly. That's basically a a script that can do anything you want and communicates back to Consul via its return code. We also support HTTP checks, TCP checks. We have a time to live, kind of a dead person switch check. So with that type of check, you register it with Consul, and then your application has to service it on a periodic interval. Otherwise, Consul will mark it failed. So even if your application dies completely, Consul can detect that it's failed. And architecturally, the agents, and we'll talk about what agents are shortly, they run the checks locally on each node in your cluster, and they only push service state changes to the Consul servers. So it's unlike other systems where you have a central entity that's shelling out or SSHing out and polling a number of servers. With Consul, all that activity happens at the edges, and then only interesting sort of deltas are sent to the servers. So it scales really, really well. And the nice thing about Consul unifying health checking with service discovery is that it can tie those two things together automatically. So when you ask for a healthy instance of a service, or when you ask for an instance of a service, you'll get a healthy one, not one that's failing its health checks. And that's handled all automatically under the hood by Consul. And then the third pillar is high availability. So Consul's designed to scale to multiple data centers with minimal configuration, almost no configuration. And it allows you to look up services in other data centers, or you can prefer local services, and we'll see some interesting applications of that. And we'll see in the prepared query section, you can manage really complex failover policies. You can find the next closest by round trip time service if no local services are available, things like that. And then with the locking primitives, you can coordinate complex systems within a data center. So you can have sort of leader-follower type designs. You can have a master with an automatic failover. Consul provides you tools to implement those types of features into your own services. So here's a very basic service definition. I'm not going to go through this in tons of detail, but it gives you an idea of how you'd register a service with Consul. So in this case, we've got a Redis service that we've registered. We've given it the name Redis. Consul has the concept of tags, so you can use those to look up. You can find a Redis slave or a Redis master, and those can be manipulated from external systems if you want to reflect the current state. As we said before, you register a port number. And then in this example, we run a check Redis script that runs every 10 seconds. So whatever that Python script does to check Redis, it'll report back, and that's what will control the health of the Redis service according to this definition. So say that this has been registered with Consul. How does some other piece of software in your cluster figure out where Redis is? Here's an example of sort of the most basic integration, and that's through DNS. So we can look up slave.redis.service.consul. So slave is the tag we define, Redis is the service name, the .service.consul is a special subdomain that Consul handles. And you can see that it gave us in the answer section, we've got an IP address there. We also support things like serve queries. So in this case, we've also discovered through DNS that it's listening on port 8000, and we've gotten an IP again. So that's just kind of a really high-level walkthrough of the basic sort of tenets of Consul and the basic feature set. Let's dig in next to Consul's architecture and learn about how this stuff is put together under the hood. So at a high level, each node in a cluster runs something called a Consul agent. So Consul agent is based on a single Go binary. It's one binary that you run everywhere, and most of these are in client mode. So what a agent in client mode does is it manages all the registered services and health checks on a given node. So you run one basically Consul process on each node in your cluster, excuse me, and it'll manage all the services and health checks for that services that reside on that node. It participates in a gossip protocol, which is sort of an underlying mechanism that all nodes participate in to, one, they randomly ping each other over UDP and TCP to just get a basic liveness check of the node. Is this node responding to pings? Does it appear to be there? And there's a set of steps that the Gaza protocol will go through to suspect that a node has failed, confirm that it's failed, and then gossip it around the cluster. So in this way, the Gaza protocol lets changes propagate really quickly about members leaving and joining the cluster, and about the health at a basic sort of ping level of all the nodes in the cluster. Excuse me. And the nice thing about the Gaza protocol is it's basically like a fixed level of traffic for your cluster, even for any size cluster. So it automatically scales the rate that it does gossip, and there's sort of a fixed cadence of the pings. So this is kind of it's a scalable sort of background level traffic that carries out this function for Consul. And then when an application does a DNS query or makes an HTTP request to its Consul agent, the clients will forward the request up to one of the Consul servers. And we'll talk about what servers do next. Excuse me. And then one nice thing here is that the clients keep track of which set of Consul servers are available, which ones are alive. They manage all the connections for you. So a lot of people who are new to Consul want to try and put the servers behind a load balancer. That's something that you never need to do with Consul. As long as you're speaking, you have all your applications on a given node, talk to the client agent on their node, they'll figure out where the servers are, when the servers are alive, finding a new healthy server if a server goes away. All that's managed for you. So you don't need a load balancer. You don't need to add a sort of single point of failure in front of Consul. It makes it a resilient design, and it's simple to configure. And then you'll have, in a typical cluster, you'll have 3 or 5 agents in server mode. So these do everything that the clients do, but they add additional functions. So the main distinction for the servers is they manage the state store, which is driven by wrap as a consistency layer, basically to store the key value information, things like sessions, ACLs, all the sort of centralized state of the cluster is managed on the servers. And you'll usually have 3 or 5, depending on your level of failure tolerance. So if you have 3 servers, you can take any single failure and keep going without a disruption to your cluster. And if you have 5, you can take 2 failures without any disruption. So that's just based on your availability needs. And the servers will forward client requests to the leader if necessary. So if a client agent wants to do a write to update a key, it will talk to any one of the servers. And if that server is not the leader, it'll internally forward the request over to the leader to perform the write. So let's look at a sort of concrete example with this simple cluster. So we've got 3 client agents up at the top. So you can think of these as just VMs running some applications. They might be running web servers. They might be running Redis. They might be running, whatever your sort of business stuff is. And then you have 3 server agents. So these are separate VMs or physical machines or whatever that are hosting your Consul server processes. And usually these are sort of on their own or combined with other sort of cluster management tools, but aren't typically running application software, although there's no reason they can't. And one of these agents is the leader. So at the first level, we'll talk about LAN gossip. So this actually occurs between all agents in the cluster, and basically on a periodic interval, each agent will pick another agent to probe. It'll send it a ping over UDP. If that fails, it'll try TCP. If it doesn't hear back, it'll actually ask peers. It'll ask other agents to ping it on its behalf. And then if enough time passes, it'll declare that it thinks that a node has failed. And then the pinging is one aspect of this, and then there's another phase which is sort of gossiping each agent's understanding of the rest of the cluster state around. and it'll converge on basically a list of agents that it thinks are present and what their health status is. So this is kind of going on in the background. As a user of Consul, this isn't sort of directly exposed to you, but it's important to understand what's going on here. And this level of sort of discovery of other nodes and whether they're healthy or not does factor into service discovery. So if one of the agents is determined bad sort of at this gossip layer, then the services on that agent's node will be shown as unavailable in Consul. So they'll be taken out of service. And then in sort of the data flow layer, so imagine that the gossip is happening underneath. This is the flow of information for sort of a sample interaction with the KV store. So if you look at the top right, the client agent, some application on that node is doing a key value update. That client agent makes a remote procedure call, one of the server agents. It doesn't know who's the leader, it doesn't really care. It just forwards it on. That server agent in the bottom right corner is not the leader, so it forwards that RPC on to the leader, which makes an update to the state store, and then you can see in the bottom the two Raft replication arrows. So it updates the other two servers in a consistent way using Raft. And then in this case, we've got the client agent in the top center. It's doing a blocking remote procedure call, so it's waiting for that particular key to get updated. So we see that it's got sort of a long pole operation that wakes up and gets a response, and some application on that node gets a key value notification, so it learns that that key has been updated. So that's kind of a basic interaction with Consul from sort of a plumbing perspective. And because there's so many moving pieces in Consul, sometimes it can be hard for people to have a good handle on kind of where the source of truth is in Consul. So who really holds the source for different pieces of information. So this is a kind of a summary of that. One thing that's sort of a common question is about service registration and health checks, because the Consul servers have a catalog. And when you do a DNS request, it ends up getting sent to the servers under the hood. And they know sort of the canonical list of services and what's healthy, what's not. But the actual source of truth of that is in the agents themselves. So when you register services, you register with your local agent, and then that takes care of syncing it back to the Consul servers. So even if you wiped out your Consul servers completely and set up fresh new ones, as they learn about the different agents in the cluster, those agents would sync all their state back and basically recreate the service catalog in the servers in a few seconds. So it's robust because that information is distributed around the cluster, and it's an interesting design. And it's interesting because there are two different APIs. There's a sort of the V1 agent API. That's where you should register services. That's registering things locally with the agent, which gets synced back to the catalog. If you look in the Consul documentation, there is a catalog API which also lets you register services. That's kind of what's happening under the hood by the agent, but that's not something you'd use directly to write entries to unless you were doing some kind of custom custom tooling around Consul, or you're registering external services that aren't part of any node that's in the cluster. But typically you just use the agent API and it'll take care of all the syncing for you. All the other state is held by the Consul servers. So key value stores, key value entries, sessions, ACLs, all that is stored in the central state store handled by the Consul servers. And as we saw in the previous example, the agents make RPC calls up to the servers to get this data. And if you have ACLs turned on, the servers enforce the ACL rules for reading and writing, sort of within the server boundary. One interesting thing, as we saw in the previous example, there were 3 servers. The client on the right had picked the server on the right sort of randomly. If your application can tolerate it, there are different tunable consistency modes. So you can get horizontal read scaling across all your servers if you can handle the results being stale on the order of a second or so. That's typical replication lagging for a busy cluster. Um, if you require consistency, then even though your clients are potentially talking to all the servers are going to be internally forwarding everything to the leader at all times. So it's an important thing for scaling. If you want to get read scaling across your servers, is to relax your consistency modes. And that's available for DNS queries, and it's also available in many of the HTTP APIs. All right, so our next topic will be a distributed lock use case. So this kind of taking what we know about Consul so far, this is one set of applications that you can use on top of Consul's key value store. So here's the use case. You've got multiple instances of a service running within a data center. You only want one or n instances running at any given time. N is often one. You want one sort of active one, and then you want several standbys available that can jump in should the active one go down. And the key thing is processes may die and not give up their leadership gracefully. So it'd be easy if things that were going to fail would tell you they're about to fail and give up their leader status, but sometimes the machine just gets, powered off or dies. So Consul's solution for that is its capability for distributed locks. So this capability is built into the key value store. It does the leader election client side, so the servers coordinate it, but basically the clients set it up. So you don't have to configure your servers any special way. It's all sort of driven by the client. It does support a semaphore mode, so n can be greater than 1. So you can have sort of a mutex mode where you say, I only want one of these in my cluster running at any given time, or you can say, I want 3 of them, whatever n you want to set there. It's baked into Consul's Go API client library. So if you're writing a Go application, it's really easy to sort of have a first-class implementation of this right in your code. You can use our HTTP libraries directly, or we'll show in the next slide, you can just use the Consul lock command. So this is an example using Consul lock for a singleton version of a service. So this foo is basically an executable you want to run. The service foo lock is a path in your KV store that these different instances will use to coordinate. And Consul lock is a built-in CLI command for Consul that will do the setup of the lock. It'll manage getting the lock and making sure you have it before it executes a process. And it'll manage monitoring and registering a session for that lock to detect when things fail. So we see in this example, the node 1 runs the service, and it sort of maintains the lock in the background. And then node 2 is our standby. Consul lock, in this case, is waiting to get the lock before it executes the foo process. Here's another example. This is built into an application called Consul template. So what Consul template is it's a standalone tool that you run. You configure it with template files that reference things like your service catalog or key value entries. It'll watch for those to change. Whenever they change, it'll render a configuration file and then run a command, usually to restart a service. So an example, say you're configuring a set of load balancers. So you have a template that iterates over all your services, writes an HA proxy file, and when any change happens and you render new files, you send a hub to HA proxy to reload the configuration. So in this example, each sort of purple box represents a set of load balancers polling Consul for essentially the same information. So in this example, we're running the same template on a whole bunch of nodes, but each node is independently doing a whole bunch of blocking queries back to Consul to get the same information. Consul template integrated Consul's distributed locks under the hood. So basically, you add this new deduplicate command line option, and Consul template will elect a leader instance, and it does this per template. So it takes a hash of the template and says, like, anybody that's interested in this hash, I'm taking the lock, I'm going to do all the queries against Consul, I'm going to actually write the information you need to render the template back into Consul's KV store, and then all the followers can just quickly retrieve that and render it. So as sort of the thick lines on this show, this pattern has a lot of wasteful read volume against Consul. This version has basically the minimal read volume possible. So it's much more efficient to scale with this. And then basically you just add the command line option and it just works. That's pretty cool. So this is doing the same thing that the Consul lock command did sort of externally, but internally and baked into a Go binary in this case. And I mentioned sessions a little bit without talking about what they are. Under the hood, when you run Consul lock, and even in the case of the Consul template example, when you create a lock, you first create something called a session, which is tied to your node. And when you take the lock, you say, hey, this lock is bound to this session. So if any health check on the node fails, which includes that gossip-based check, so you can power off the node, and then eventually, within a few seconds, the cluster will figure out that node is no longer there. It will fail that node's gossip sort of health check, and then that will cause the session to expire, which will cause the lock to be given up. So all that happens basically automatically by Consul. One nuance, if you're using locks and sessions, is that Consul has something called a lock delay. And this is kind of a mandatory waiting period that is imposed if a lock is given up ungracefully. So if, say, you shut down a process and it gives up its lock cleanly, that's not subject to the lock delay. But if your node dies and your lock is cleared, is given up because your session expired, then there's a lock delay which you can tune, which is basically a mandatory waiting period, which helps give a leader who's malfunctioning time to realize that they've lost the lock and stop writing. So this is inspired by Chubby locks from Google. Has a similar delay, and it's something you can tune. So it sets the quickest recovery time in the event of a sort of ungraceful lock release, but you want to tune that to a safe period to make sure that you don't end up with consistency problems. So it's just something to know about. There's pretty good documentation in the Consul site that goes into more detail about this. So that first half went through sort of the basic single data center Consul architecture, how data flows around, and then a use case around distributed locks. We're going to revisit Consul's architecture now in the context of multiple data centers. So when your cluster spans usually sort of different geographic regions or different sort of significant physical boundaries, you may want to use Consul's concept of a data center. And what these do is they let you run independent Consul clusters. So each set of nodes will talk to the other nodes within its data center, and you'll run a different set of Consul servers for each data center, but you'll link the servers together in a way that provides some really useful features. So the Consul client agents don't really change. They're configured to be in one of the data centers that you've got set up. But any Consul agent that's in server mode gets linked together to form a distinct WAN cluster. So this behaves just like the gossip and ping protocol does kind of within the data center, except that the timing is relaxed because it's expected that these are over sort of long, high latency links with potentially a little bit more packet loss. and the pool of servers is a different pool than sort of the pool that exists within each data center. So when we summarize it, we say within a data center, you want everything to be a fully connected mesh. And then between the data centers, you need the server agents to be in a connected mesh to do this WAN clustering. And the one new detail about what server agents do when you have multiple data centers is they'll forward client requests to servers in other data centers. So we'll show that through example here with a sample cluster. So here's our basic example, sort of broken out into 2 different data centers. So we've got 3 client agents in each data center, 3 servers in each data center. Each data center has a leader, server, so similar pattern, but now we have 2 of them. Within the data center, remember, everything's the same. Now this is sort of the new dimension we talked about, which is the WAN gossip. So this happens only among the servers in the different centers, but they're doing the same thing. They're randomly probing each other with UDP and TCP pings. They're gossiping the list of available server agents that they've discovered. They're declaring, hey, this one looks like it's failed. Yes, I think that one has failed. So they're doing all the same stuff that happens within the data center, but just among the servers in the WAN. And then for the WAN data flow, here's kind of a work example where the client agent in the upper right, it's doing a similar KV update, but it's updating a key in a different data center. So data center 1 agent is updating a key in data center 2. So the application, it just makes a request to the client agent on its node. It does have to specify that this is for data center 2 when it makes that request. That makes an RPC call to one of its server agents in data center 1. That does a forward over the WAN, the RPC call to a server agent in data center 2. And then that sends it on to the leader. So it's pretty cool in this case that the client agent didn't have to really know much about the details of how its request was going to get there. It's mostly transparent, except that it's saying, hey, this is a key over there, set this somehow. And then the raft replication happens in data center 2 side. Note that the raft replication only involves the servers within data center 2. So at the raft level, there's no interaction across the WAN between the servers. It's all RPC forwarding. And that gets us into sort of the WAN edition of our sources of truth slide. So within each data center, everything's the same. And then between data centers, remote requests are forwarded. So one common question is key value data. Is this replicated? It's not by default. So each data center has its own key value store that's independent. It has its own service catalog. All that stuff is independent. There are some tools. For example, we have a tool called Consul replicate that will let you replicate the whole key value store or pieces of it between your data centers if you need that. Another common use case is to have that sort of information in Git and then have a tool like Git to Consul that plumbs that into your KV store. But by default, the different data centers are all independent. And then for ACLs, those actually live in a single ACL data center. So if a token is supplied, the policy for that token is always fetched from the single ACL data center, one of the servers there. But there is a caching layer, which makes that efficient, because that would be horrible if you had to go across the WAN for every request. So there you can configure caching, and you can also configure how your cache policy works in the event of a partition. So you can allow the cache to basically extend if needed to handle the case where your WAN is down. So building on the architecture that we discussed for multiple data centers, we'll look at a use case around something called prepared queries. These were newly introduced to Consul in version 0.6. So here's the use case. You have multiple instances of a server, and those exist in multiple data centers. So you've got a geographically distributed set of services. For this example, clients can talk to any of them, but they want to talk to the sort of the fastest ones with the lowest latency if possible. And policies can change, and it's really desirable to not have to teach your clients about all these details. So you don't want to have to go in your application code or the code for your services and teach them all the places they could look for a given instance of a service. You want that to be as simple as possible. So in Consul 06, we introduced something called prepared queries. So this creates a new query namespace similar to the service namespace. You register queries against the different parts of this namespace. So you can create new names and say, when this name is accessed, run this query and supply the results using this definition. Just like all the other types of service discovery, clients can use an HTTP API, or they can just use DNS to run these queries. And there's quite a bit of functionality under the hood, so we'll go through some examples that show what's possible. So here is an example of a really basic sort of Redis with failover query. So we've registered a new name called GeoRedis slave. It maps to a service name of Redis, and we have a failover section that says nearest N3. And we'll talk a little bit more in a sec how that works. And then we said choose a service with the tag slave. So, and you can see this is a sort of a curl example. So this is a query definition that's created by posting against this query endpoint. And what you get here is a client can look up something like georedisslave.query.consul, and it'll just work. So when a client fetches that, it'll look for a Redis service instance locally, and if there aren't any available locally, it'll go out to the next 3 other data centers that it knows about in the WAN, and it'll do that in a priority order based on round trip time. So, and we have a little more detail later about how the round trip time stuff works. But that's quite a bit of power to put just behind that name. So some service that was previously looking for slave.redis.service.consul in our sort of early example can now just stick this name somewhere in a configuration and get this failover behavior. It's pretty transparent other than just the name change. In Consul 064, which we are releasing this week, hopefully, we released a release candidate last week if you want to play with this. We introduced the concept of prepared query templates. So these add quite a bit more power. One piece of feedback we got once we released prepared queries was that people said, hey, I've got hundreds of services. I want to apply these types of policies to lots of them, but I don't want to manage hundreds of queries. Can you give me something a little more flexible? So we created templates. So I'll have 2 examples of templates here for you. So this one, you can see it's got a new template section, and it says the type is name prefix match. So this will match any query that starts with geo-db. And then once it matches that prefix, it'll apply the regular expression, which is basically pulling a few pieces out based on where client's dash is. And then it's substituting into the service selector using kind of an interpolation syntax, which is we base this on our HashiCorp interpolation library, which is also used for things like Terraform, so this might look familiar. So it's taking the first match and substituting that in with MySQL dash as the prefix. So that is basically synthesizing the service name based on part of the name. It's doing the same nearest end kind of thing. In this case, we've also thrown in a couple data centers. So it says, like, try the 3 closest ones, but make sure you also try these 2. only passing. This is just to show some more options that are possible. So this says like, only give me ones that have passing health checks. Don't give me anything that's in a warning or a critical state. And then we're taking the rest of the match and putting that into to the tags. So in the example queries, this would respond to something like godb customer master.query.consul, and you'd end up looking up a service called MySQL-customer, and you'd look for a tag master for the first one. So this is quite a bit of functionality, and the regex capability lets you maybe sort of back into a legacy naming scheme or create sort of more flexible patterns. But this is possible with prepared query templates. And then sort of the sort of ultimate is the catch-all template. So this is similar to last time. Notice that the name is empty, and I didn't supply any regular expressions here. And this basically just takes the name, the full name, and sticks it in the service name and sets nearest end to 3. So with this single template, if you register this, and it'll do a longest prefix match, so you could have more specific policies for certain services, but this basically creates a fallback where anything.query.consul will have a geo failover policy applied to it to look in the 3 nearest alternate data centers before giving up. So this is a pretty amazing set of functionality in a very, very simple form. So an application that was formerly looking for redis.service.consul, if you change that to redis.query.consul, it'll have geo failover, and your application doesn't really have to know anything else other than use this new name, and it'll magically do failover stuff. All right. And how does nearest end work? Under the hood, that's using a feature we added in Consul 06 called network tomography. So because the nodes are all pinging each other as part of their normal gossip protocol, we already had sort of an actual round-trip time measurement to each node that's taken at a fairly frequent interval. So we use, there's a set of academic research sort of under the name of Vivaldi, which is it's basically a set of algorithms for feeding those round-trip time measurements into basically a physics simulation, kind of based on masses and springs. So when you learn that a node is a little closer than you thought, then you might pull towards it. If it's further away, then you might push away from it. And what you get is a set of coordinates that let you estimate the round-trip time between any nodes in your cluster by just performing a simple calculation. So these aren't typical coordinates in the sense of like a 3-dimensional thing. They're actually 7-dimensional, and they have a few other adjustment terms like a height and an error term. But conceptually, it's very similar to taking the distance between 2 3-dimensional points. Like it's a similar square root of the sum of the squares kind of thing with a few other sort of fudge factors added in. So once this has been running for really just a few tens of seconds, you get a model that's pretty good. And then it just continually updates over time without adding any overhead for this new feature. And you have this nearest neighbor routing model that you can query. So the nearest end, when you're defining that in a prepared query, that's basically based on this model that's being updated all the time. So if something happens to one of your, say, WAN links, and it's the round trip time goes way up, it'll automatically realize that, and if it was sending traffic to that data center, it might choose an alternate data center if the round trip time comes in better. So this all kind of happens under the hood automatically. As we saw in some of those examples, you can also just specify a list. So if for some reason you don't want the closest, you want a specific alternate data center, you can configure that too. But for the most part, it's really easy to say, hey, try the next 2 closest ones and figure it out. This is slightly gratuitous, but this is an animation showing the algorithm. This was basically we synthesize an artificial pattern of nodes with round trip times that arrange them into a grid, and then ran the simulation on them. So this was just kind of an early test case, but it gives you a sense for how the algorithm works. So the nodes all sort of have no idea where they are. They sort of start out bunched up in the center, and as they get some ping information, they start to spread out and learn where each other are. And if you could see this over time, it would vibrate and wobble a little bit as they adjust, kind of within the error capabilities of their ability to measure the round trip time accurately. All right. And with that, we'll step into a really quick demonstration. So, hopefully that's visible to everybody. So what we have running here is I'm connected up to our demo cluster, which this is something you can play with. You could probably even figure out how to troll the demo if you go to demo.consul.io. And it's got 3 different data centers, one in New York, one in San Francisco, and one in Amsterdam. Each one is running a Redis. Each one is running 3 nodes, each node running a Redis server. So right now we're in the New York data center. We're looking at the Redis service. We have 3 clients that are all running Redis. Here's their IPs. And they run a Redis check every 10 seconds, which does a simple TCP connect to the port to make sure that the server is still there. And we can show, if we switch over to San Francisco, similar, we've got 3 instances in San Francisco, and in Amsterdam, excuse me, we have 3 instances there. So in this screen, I'm on one of the servers in the cluster. I happen to be on one in New York. And I've got basically a watch running dig against Consul for redis.service.consul. And this is running once a second. You can see this set of IPs matches the set we see here. It's updating once a second. You can see these guys kind of shuffling and sparkling, so it's choosing 3 in an order that's random. Every request gets a different shuffle, so it's doing load balancing. And let's see what happens when we fail some of the services. So each of these panes is logged into one of these clients, and I'm just going to do a really simple Redis server stop on one of them. So the health check for Redis is running every 10 seconds, so it might take a few seconds to have the results reflected over in the DNS query, but we just saw that that one was taken out of rotation. Let's do another one. So we'll kill another one. So we should see that drop off. And then finally, now we've killed them all. So when you run redis.service.consul DNS query inside New York, you're stuck. There's no healthy instances left. So let's bring them back while we talk about the next step here. Okay, so brought them back up. We've got some healthy Redises coming up, so things look good again. There we go. So now in this cluster, we've also registered the catch-all prepared query. So we can see I'm running this is the V1 query endpoint, so this lets me see the list of queries that are defined for this cluster. So this is the query ID, so we can just remember it ends in C9. It's got an empty name. It's a prefix match template. It takes the full name and puts it in the service name. and it looks in nearest 3 for an alternate. So one thing I can show you here is we've got an explain endpoint. So I can basically take anything .query.consul that I would supply and put it in here, and we can see which template or which prepared query matches. And then in the case of the template, we can actually see sort of the realized query with all the substitutions made. For this one, it's pretty simple. It basically takes this and sticks it in there. For the more complicated case with a regular expression, this is a useful tool for seeing what happens, making sure your substitutions make sense. It lets you see what your prepared query definition looks like for a template after it's been rendered, basically. You can also execute a query by name here. So if I run the redis.query.consul query, then I can see that I get some healthy nodes listed in here. I get back the check information about those nodes. So I'll do a little bit of collapsing just so you can kind of see this structure better. And then because this is a prepared query, I get some information about who answered it. So there were no failovers, and these results came from the NYC3 data center. So let's go back here, kill this, and basically change this to run the prepared query. So in this case, you could imagine that this is a query that I did. I'm sorry, this is a change I made to one of my services. I reconfigured it. So instead of using redis.service.consul, which only looks locally, I say, hey, use redis.query.consul. It does all the magic stuff you want. Just use that. So this was basically the only change I had to make to my application, was to look up a different host name. Now let's start killing stuff and see what happens. So we'll stop one of the servers, drops out, stop another one. And remember, this is on a 10-second health check interval, so the speed from when I kill it to when it gets detected is a function of that. You could certainly dial that down. Kill a third one. So at this point, when we did redis.service.consul, we were done. We were out. In this case, we've got some new IPs. So let's see what's going on. So we'll execute that now that we've killed all the local services. So if I refresh this, I should be able to see all the Redis checks are failing in New York. I'm going to re-execute the query, and you can see I'm getting different node names now. So we did one failover, and the data center that answered is Amsterdam. So we've got a set of 3 healthy Redis services that we're load balancing across in Amsterdam from the perspective of the New York data center, and basically we got all that by just changing this name. And an interesting thing is, why did it choose Amsterdam? And we can actually do a quick query here. So if I can run this consul RTT command and look at the ping time as understood, the round trip time as seen by Consul from New York to San Francisco, it's seeing that as 89 milliseconds. And from New York to Amsterdam, it's 80.4 milliseconds. So that's why I chose Amsterdam. If that relationship was to change, then it would start to use San Francisco servers here. And that's all kind of just baked in by the network topography. And as soon as we get a healthy instance back up in New York, we'll fail back over to that guy and stop using the WAN links there. So we'll put it back to normal. And now whatever event it was. The kill Redis in New York is now passed, and our clients have automatically shifted back to their local New York Redis servers. And if we refresh this, we should see that there's no longer any failed over responses and everything's coming from New York. So that's kind of an end-to-end demo of prepared queries. Shifting back here. So before we close the presentation part, there are some links to more information. There's the Consul homepage. We recently launched Consul Enterprise, which is definitely worth a look. The community page has links to the mailing list, where we're at on IRC, other information about contributors. And then the tools page is interesting. I was looking today, there's over 20 tools on there now that integrate with Consul and over a dozen client libraries for Consul. So there's quite a bit of community support around Consul. And that's only things we've listed here. There's actually a lot more. So that is it. So I think we'll move into the question phase. Thanks for watching.
Thanks, James. That was fantastic. And thank you to everyone that's been asking questions. James, if you take a look, there's been some pretty good questions. So it's 11 o'clock now. I think we'll spend the next 10 to 15 minutes trying to get through all these questions. And then if we don't get to all of your questions, we can follow up after this webinar. So James, I'm just going to start from the top and just kind of go down, if that's all right with you.
Yep.
So Zach had a question. Is there a way to disable the surf protocol / gossip layer?
There is not. So that's sort of a fundamental, that's fundamental to how Consul bootstraps new nodes. It's fundamental to how the health checking works. So that's a required part of Consul. It's deeply baked in there.
Okay, great. So David had a question. Are there any network concerns around large Consul clusters with regards to the gossip protocol?
The gossip protocol is designed to scale back based